Hi everyone, this is chapter 9 of Astro, and this is the family of stars and learning about the characteristics of the stars in the universe. We've already studied our star, but that's like studying yourself, and now we have to study the family around it. So let's go into it a bit. We've already studied our stars for distance and diameter, volume, mass, temperature, composition, velocity of rotation, velocity of orbit. You'll recognize a lot of the methods that we use to study our star. We're going to be using them to study all the stars in this broad family that we have of stars. So I just thought I would let you know that families are complicated, and so that while we just studied our star, our individual star, when we're studying billions of stars, we need more methods, we need more classifications for those stars. So we're going to be looking at a lot of the same characteristics, but we might be using some different methods or some different classifications for them so that we can put these family members into little classifications. Like some are the shy people and some of the outgoing people, and some of the people are silly and some of the people are really bored. And so we want to put them in and sort them out. We're still going to be studying distances, a new characteristic called luminosity. We're going to still be studying temperature and size and mass and velocity of orbit. So let's get into distances because we have some new methods for that. Now, the methods that we have are still all based on triangulation. Oh, I have to change that spelling up there. But they're all still based on triangulation. So these methods that you're used to from triangulation are just being extrapolated. We're going to talk about radar arranging. We're also going to revisit parallax, and we are going to be talking about main sequence fitting. You'll hear that today. And we're going to be talking about luminosity for distances. So different methods for these stars that you don't see quite often, like the family from far away that you don't see very often. So let's get into that. You already know about triangulation. We're going to do a brief review of it, because everything is based on triangulation. And so if you are looking at a tree and your friend Sue is looking at a tree, the same tree, you see that tree from different angles and you see what is behind it in different ways. You studied this in your lab. Just to go over how you can measure the distance to that tree, you can use this 90-degree angle. You can use the angle of your friend Sue. Now you have two angles, and you know the distance between you on the baseline, so you can use trigonometry. So you can say if your friend Sue is at a 60-degree angle, if you did the tangent of 60 degrees, that would be opposite over adjacent at 2 meters for a baseline. Let's say the baseline is 2 meters. And you'd get a square root of 3 as the tangent of 60 degrees. Then you'd solve for the opposite, and you'd get 3.46 meters is your distance. Okay, so this is the basis of triangulation and the basis for all the methods that we use as they give us the precision that we need throughout the universe. For instance, with radar reflection, what is really interesting is that there is a radar reflector, a number of them, left on the moon by Apollo. And so this is, of course, my favorite telescope, the Keck telescope in Hawaii, sending up laser beams to use triangulation to plot the amount of time it takes to send a laser beam to the reflector and get it back. And if we take that total time to and fro multiplied by the speed of light, which is the distance that the light goes over time, then we can cancel out the time and we can get the distance to and fro, divide that by 2, and we have the distance to the moon. Okay, that's radar reflection. We can do that in the inner solar system. We can do that to Mars. We can do that to the moon. I think Mars is about as far as we've gone with radar detection, or reflection, I should say. When we go farther out than our solar system, we do use trigonometric parallax, which is a triangulation just like you were looking at in a slightly different way. So just to go over this, you did this in your lab where you looked at a star and you looked on stellarium from that star, and you noted that the star was in a certain point in a constellation. Then you went 6 months later and you looked at that star from July, or 6 months later, and the star looked at it like it was in a different point in the constellation. So you've done this. If you wanted to find the distance to that star, you'd have a set of 6 steps where you'd measure the total angular diameter from your January observation of the star to your July observation. What is this angle? And then you still want to get a 90-degree angle so you can use your trigonometry real well and take advantage of that one angle. So you cut this angle that you made in half. And when you cut that angle that you made in half, one of those halves becomes your stellar parallax angle. Okay? And you know that over the course of 6 months from January to July, you went from 1 astronomical unit distance to the sun all the way over here, and you traveled, and now you're at the opposite side. So you've effectively gone 2 astronomical unit distance from to the sun in 6 months. 1, 2. So if you divide this angle in half and use this right angle, you've used 1 astronomical unit distance as your baseline. All right, so you have an angle, you have an angle, you have 1 measurement. Now you can do tangent of P is opposite over adjacent, and you can solve for D. And that is going to be your distance to your close star. This is your close star in astronomical units. Alternately, you could use kilometers in here, and then you get your distance in kilometers. I just told you that. And one of the things that you come upon with this is that these angular diameters that you're noting in the universe are so infinitesimally small. And in fact, if you are measuring things, you're measuring things in arc seconds. You might say, what is an arc second? An arc second, think about this. A circle is 360 degrees. Obviously, this 1 degree is not to scale, right? There's 360 degrees in this circle, but we need to blow that up a bit, because you are taking, when you take an arc second, you're taking 1 degree, splitting it into 60 degrees, and then splitting it again into 60, and you've got less than 1 arc second, which is 1/360th of a circle divided by 60, and it's less than that. The nearest star to the Earth shows a parallax of 0.76 arc seconds. Very difficult to measure, and it's fraught with some issues. So that sometimes we try to make it a little bit more mathematical, and what we can do is, if we get that angle, we can take that inverse of the arc second angle, 1 divided by the arc second angle, that P, gives us a distance in parsecs. Now you might say, what is a parsec? A parsec is short for a parallax arc second. Before, we were talking about parallax angles. This is actually a measure of distance in parsecs, which gets away from all the exponential use of kilometers. And what we're saying is that a parsec is about 3.26 light years. And that's a lot better than using a lot of exponents there for kilometers. If we take the closest star that we've got, our closest star, which is Alpha Centauri, would be 1 over an arc second of 0.6. That's 1.32 parsecs away. Well, how many light years is that? 1.32 parsecs times the conversion factor of 3.26 light years equals 1 parsec. You can cancel out the parsec. You can cancel out the parsec. You're left with 4.29 light years away. 4.29 light years away for the closest star to our sun. So we're trying to use more math and fewer exponents when we use some of these formulas and some of these units. There are still problems with parallax. It may have a little bit of subjection to the observer. If you saw something in January and then you saw it in July, you might have a different view. You might have a different lens in that telescope. So it could be subjective to the observer, but the big one is that there's blurring due to the diffraction in the Earth's atmosphere, which you've learned before when you were studying for your telescope. So these are very small parallax angles, and sometimes we need other ways and methods to measure them. But just to give you an idea of the solar neighborhood, the 30 closest stars to the sun, remember Alpha Centauri was less than 1 parsec, or about, 4.24 light years away. So in other words, this is quite close to the sun, less than 1 parsec. Here's my 1 parsec line, less than 1 parsec in here. And the others are quite a bit farther away. I think the nearest one I see is right around here. Yeah, Barnard is the second one, is the second closest star, and it is out close to 10 light years away. So there's a very big difference. That gives you a feel for what's going on, and I'll see you on the other side.